Good morning or afternoon or whatever it is for you, physical science class. This is kind of something to go along with 16B. I'm going to have a video for you on parts of the atom and working on isotopic notation, but I wanted to go over some of the slides with you because there's some things that have to be filled in. And so this is just kind of supplement all the material that I've given to you. So as we look at this, the first thing we have here is to illustrate a proton and neutron quark. There are some slides on this, but I'd kind of just like to kind of give you an idea of an atom. Normally in elementary school, as you've done your reading, you should have come to the point where you realize that in elementary school, they give you like a solar system model of an atom where you have a nucleus and then on the outside you have electrons orbiting around it like planets go around the sun. That's not quite how it works, as you saw that we have the quantum model where you have a dense nucleus and then electrons travel sporadically in a cloud throughout the atom. So if you have an electron out there, and as Heisenberg said in your notes, if you look at the position of an electron, its charge will change, and if you try to observe its charge, its position will change. And a lot of that has to do with equations about momentum. And so the quantum model would be very hard for me to draw because it's like a basketball, and electrons can come any place in an electron orbital around it. So, but that's the point today is we want to focus on the nucleus. So I'm going to go back to the solar system model just for a second. Now, you got to remember that this is not how an atom really works, but outside of the dense central core, you have electrons. Electrons have a charge of -1. And then in the inside, I'm going to represent the inside with a couple of purple dots as being protons. And I'm even going to, so you have protons in your nucleus. I'm even going to put a positive side inside of those to say your protons have a positive charge. Then also you have neutrons, and neutrons have a neutral charge. They have a charge of 0. So if I were to look at this element here that I've got, this atom, it has 2 protons, which would give you a positive 2 charge from the protons. And those are represented by those purple dots. And it has a -2 charge that comes from the electrons. And the electrons are represented by those orange dots that are located on the outside or the orbitals. This diagram is not drawn to scale. Electrons are so much smaller, you can't even compare them to protons and neutrons. How they know that? It took someone a lot smarter than me to figure that out. But what I'd like to do is I'd like to talk to you guys about quark theory. That's something the book talks about. It's an interesting concept. But I was talking to somebody. We were talking about dividing a cake the other day, and I said, how many times can you divide a cake? And they said, oh, probably about 5 or 6 times. Yeah, if I were dividing a cake, I couldn't divide it very many times personally, but as a scientist, you can divide it, and you can divide it, and you can divide it, and you can divide it. And it's possible to divide and divide and divide and divide and divide. Sometimes I wonder if the division process, at least from man's perspective, is limitless. Like you can keep dividing and keep dividing things and keep dividing things. So right now we're to the point where we think about subatomic particles. You've heard of. This is something that you learned about in science class before. Protons, neutrons, and electrons. Now, scientists have said we can go smaller than the proton, the neutron, and the electron. So what I'm going to sketch for you is a diagram of a proton. Now, this is a theoretical diagram of a proton, and I was looking at some diagrams of protons just a few minutes ago. It doesn't quite look like this, but this understands the concept. So what we're going to do is we're going to just divide this into thirds, like 33%, 33%, and 33%. And also, we're going to look at the neutron. These things are located inside the nucleus of the atom, right over here. That's where your protons and neutrons are. And each one is divided up into thirds. And within there, we have two different things. We have an up quark and we have I'm trying to decide what color to do, down quark. The charge of a down quark is -1/3. So think of its electrical charge as being -1/3. An up quark's charge is +2/3. Okay. Now, just because the up quark is underneath the proton and the down quark is underneath the neutron, they both contain up quarks and down quarks. So try to help you understand this process. What I'm going to do is I'm going to say our up quarks are red. So you can see a proton has an up quark here and an up quark here. So if that breaks it into thirds, like 33%, what percentage of the proton is made up of up quarks? Well, if you said 66%, you would be correct. Okay, so there's proton with up quarks, and a neutron only has one up quark. And so then, any place that's not an up quark is, you guessed it, a down quark. I think I have something on the test where I ask you to, just thinking about that. I also want to tell you guys that we're not doing a test for this chapter. We didn't do a test for the last chapter. I might throw like a test that includes this stuff on it. It's kind of an end of the year project for you guys to help you finish out the school year, especially some of you guys who might be struggling with your grades, or maybe this social distancing school has been kind of tricky for you. You'd like to get caught up. That would be a good way to do it. Okay. And the neutron is made up of two down quarks and one up quark. Okay, so this is where it kind of begins to come together. Now, just to make this a little bit neater, there, that looks halfway decent. I mean, I could probably make it a little bit better if I took my time, but you guys would probably get kind of bored like that. But the proton has two up quarks and one down quark, whereas the neutron has two down quarks and one up quark. So now I get my pen out, and I'm going to put the charges in there. Remember, an up quark, the red, is +2/3. +2/3. And -1/3. -1/3. -1/3. And +2/3. Now let's look at the total charge. Let's look for a proton. We got +2/3, +2/3, -1/3. And for the neutron, we got -1/3, -1/3, +2/3. Now, for those math whizzes out there, let's add these up. 2/3 plus 2/3 is 4/3. -1/3 is +3/3, or a charge of +1. Remember over here, I said if you have two protons, you have a charge of +2. Any proton is going to have a charge of positive 1. You say, well, why is this positive 2? Well, back when I was talking, I had 2 protons. They have a charge of positive 1. The proton has a charge of positive 1. So if we added these up, we have negative 1 minus 1 is negative 2 plus 2 thirds is 0 over 3. So a neutron has a charge of 0. 0 is the charge of a neutron. That's why we call it a neutron, because it has a neutral charge, neither positive or negative. That's kind of the foundation to quark theory, and what quarks are all about. That's where you gotta begin, and we don't have time or the energy to go any farther. Another thing that we want to talk about is isotopic notation. So if you were to look in your homework, you're going to find stuff on isotopic notation on pages 392 and 393. I'll even write that down, 392 and 393 in your book. You'll find a periodic table of elements. We're not going to get to it this year, but a guy by the name of Dmitry Mendeleev, a chemistry teacher, kind of spent a weekend looking at the periodic nature of elements, how they repeat over a given time, and he came up with this cool chart. And that cool chart made everyone in chemistry's life amazing. Plus, it predicted different elements that would be found later. So if I look on that table, I would find that what we're talking about here, if I look, number 6 on the periodic table is carbon. Carbon. All right. Now, carbon is always number 6. And that is always determined by something called the atomic number. Atomic number. What makes it carbon is that it has 6 protons. And I find that by the atomic number right there. Carbon will always, always, always have 6 protons. If it gets more protons than that, it's not carbon. A lot of the elements and their nature is determined on the number of protons. Now, the atomic number is the number of protons, and the number above it in isotope notation is called the mass number. This was something in your notes just a little while ago. I believe I put it on your quiz for Friday, so you could be ready for that. Mass number is found by this number right here. And what mass number is, you should have already read it. It should be something you're familiar with. Mass number is the number of protons plus neutrons. Neutrons. So how many protons do we have? 6. So that means I believe that probably we're going to have 9 neutrons. Not probably. We are going to have 9 neutrons. The reason being is 6 plus 9 equals 15, which is the, oops, excuse me. Oh, that was Superman there. Mass number. Mass number. All right. Now, the number of electrons. Remember the last diagram I had over here? This had 2 protons and 2 electrons. In the nucleus, the 2 purple dots are the protons, and out at the edge, those 2 orange dots are the electrons. The net charge of this is 0, because 2 minus 2 equals 0. That's kind of, elements are pretty stable when they have a charge of 0. If they don't, they're called an ion. Positives are called cations, or cations, as some people call them. And I always tell cat lovers, a cat lover is positive, because being a cat lover is a good thing. It's called a cation. And that's positive. And an anion, oxyanion, are usually what they are, is negative. Okay? And those are if you have an element that is either has a positive or negative charge because there's an imbalance in protons and electrons. And that in isotope notation is determined right here. So we have the mass number, the atomic number, and then we have the symbol. And over here we have the electrical charge. And you'll see that in a minute because this one doesn't have an electrical charge. That means it zeroes out. So that means there's 6 electrons. And the reason being is because 6, a positive 6, and a negative 6 equals 0. There's only 6, there's not really negative 6 electrons, but they have a total charge of negative 6, but these two have to balance each other out. And that would make them pretty stable. They're not an anion or a cation. Okay, here we go. Here's another element. The reason I put this on here is because this is the element Kr. If you look that up on your periodic table, you're going to find that this is the element krypton. And it really is a real thing. That doesn't mean that Superman is roaming the Earth in fear of kryptonite. But anyways, just thought that that'd be something that you could remember. Kind of was there for you to get a little chuckle out of. But anyways, remember, we have the symbol, we have the atomic number, the mass number, and the electrical charge. Okay, so if we were looking at this, what is the number of protons found by the atomic number? If you said 36, you'd be right. If you had, and no, by the way, this is krypton. And the number of neutrons, remember 36 plus whatever the number of neutrons is has to equal 68. So what plus 36 is 68. So we could take 68 and subtract the 36 to get 32. And 32 would be the number of neutrons. And then the charge, see there's nothing here, nothing there. So that means it has to have a charge that equals 0. So the number of protons and electrons has to be the same. That wasn't too bad, was it? Let's look at another one. This one's a little bit different. K. Look it up on your periodic table, page 392 to 393. I don't think anybody can say, oh, I don't know where the periodic table is, because I've written it on here a couple times. I've said it a number of times. You look that up. You could look that symbol up in K. You might think that that's krypton, but that's not krypton. It's potassium. Potassium. Find it in bananas. So this is a little bit different. Remember, we have the atomic number. We have the mass number. And we have the symbol and the electrical charge. All right. So how many protons do we have here? 19. We knew that because that's the atomic number. So the mass number tells us the number of protons plus neutrons has to equal 40. So 40 take away our 19 would be 21. So 21 is the number of neutrons. Now electrons, remember, this is, oops, black highlighter and black ray is not going to do very good. It's the eraser. Oh boy, oh boy, oh boy. Okay, let's do this. Electrical charge. Now let's get out the highlighter. Electrical charge goes right here. And right here we have a charge of positive 1. So we want a net value of positive 1. How do you know that's positive 1? Well, it just says positive 1. If it were to have anything else, like if we were to have a positive 2, it'd be like this. Positive 2. It's just because there's nothing there. we assume that it's a positive 1. They don't need to put the 1 there because usually it's going to be pretty close to whatever that number is, okay? They're going to be close to balancing out. The farthest they could be apart, the most potential that they have to be apart is 8. And that has to do with the number of valence electrons. Don't need to worry about that. So how am I going to get to, I got positive 19, and what gives me a net value of positive 1? Wouldn't it be like this? 19 minus 18 equals 1. Again, this is called a cation. Cat people should be able to remember that. It's just a device to help you remember, because you go, how do I know if it's a cation or an anion? You remember, cat people are positive. Even if you don't think so, hopefully that'll help you remember. All right, here's another one. This one's a little bit different. This is oxygen. Periodic table. You find it on page 392 to 393. Well, if you look that up, you're going to see that the 8th one on there, and if you're having troubles finding it, that's number 8, because it says it's 8 right there, is oxygen. So oxygen has 8 protons. We have to add that to the number of neutrons to get 15. Well, what plus 8 is 15? The answer is 7. So there are 7 neutrons. Now remember, here, right here, excuse me, highlighter, right there is the electrical charge. So that means that the net value is going to be negative 1. So I think that I have to have negative 11 electrons, because negative 9 plus 8 is negative 1, because that's the net value of the charge, of the electrical charge, which is right there. Okay? Okay, that's kind of basic right there. Basic little bit of isotope notation in chemistry.